thermal equilibrium problem. This is a recording, so feel free to, pause this, fast forward. I won't be offended. You can mute this. Just go all the way to skip to the ending and look at the punchline, look at the moral of the story if you want. But this is a thermal equilibrium problem, so the key is we have to understand that when these two blocks come into contact with each other, heat will flow from the hot to the cold. That's a law of physics. So what's not so obvious is that the heat that flows out of the hot and into the cold will happen to be equal. So if it was 10,000 joules of heat energy flowing out of the hot, then there will be 10,000 joules of heat energy flowing into the cold. We don't know what the heat flow is. You could call this heat in, heat out. I chose to call it heat hot, heat out of the hot, heat into the cold. Okay, and that's the basis for my whole solution. So here we go. Now I'm going to write it out in a more lengthy version. And I like to worry about my subscripts later. This is the MC delta T heat equation, obviously. The delta T's are going to be tricky soon, and you'll see. We're going to be looking up stuff in our specific heat table and everything. But I'm going to put hot, hot, and all of this. This is hot, this is hot. This is cold. So the cold, the hot is the copper, the cold is the aluminum. So now I'm going to write this out again, but I'm going to do something with these delta T's are the tricky part, these delta T's, because I'm going to have to put an expression in there. So what I'm going to do now is play out that expression. So this is still mass of the hot, specific heat of the hot, but now I'm going to do a temperature minus a temperature here, because that's what it changes. It's something minus something else. And then what I'm going to walk you through is what do we put in for the something minus something. And I think I have a student with me, and I think you know maybe how to do that. I'm explaining this for the sake of the video, and it's good to go through that quickly, but this is the hot stuff. This is the cold stuff. Okay, here we go. What am I going to do about these right here? What am I going to do about these temperatures? What goes in here? Are there 4 different temperatures? No, there are actually 3 different temperatures here. And what I want to do is write those so that they come out to be positive numbers, meaning so that this whole expression comes out to be a positive number. That's going to sound weird right now. It'll make more sense later, but I need that to come out positive, and I need that to come out positive. So watch what I do. I know that if it's the hot, I know that the hot will always be greater than the final temperature. There's a final temperature, and there's a hot temperature. And over here at the cold, I know that the final temperature will always be greater than the cold temperature. And if I'm figuring out how much the temperature changed for the hot, then what I'm really doing is there's some final temperature which is imaginary now, and I'm looking at the difference between those. And there's a final temperature which is imaginary now over here with the cold, with the aluminum. And I'm looking at the difference for those. And I know, strangely, interestingly, that the heat flow is equal for both. And we're actually going to do a lab where we prove that. It's kind of cool. So now I'm going to put all my numbers in, and I'm asking for your help with this a little bit. But my mass of my hot, what would you put in for that?
3.
Good. And specific heat of the hot?
390.
Sounds familiar for copper. The temperature of the hot is known, so I can put in 120, and we're setting up some algebra. I don't know T final, so I got to put T final. And my mass of my cold is 1 kilogram. my specific heat of the cold is this one. I really don't know.
900.
900. Okay. And final, I just have to leave as final. So you can see what's cool is now I'm getting down to just one variable. And then the cold temperature is 10. So now I'm going to do some algebra. I'm going to pause this, do some algebra, write it out. So we've done a little algebra, as you can see here. Don't freak out about the algebra. Just pause it and look at this step by step. But all I've done is I multiplied these two and I got 1170. Multiplied these two, got 900. Then I did the distributive property. This times this. This times this. You can see that down below I got this result for the distributive property. And then I got this result for that distributive property. And then I get this. I'm just walking you through the algebra. I mean, sit down with somebody who knows algebra and, you know, solve this. But what are we getting for a final result for the final temperature? I'm expecting a number between 120 and 10. My equilibrium temperature is, it's not an average exactly.
72.17.
This is my equilibrium temperature. My final answer down here. Equilibrium temperature right there. Also known as the final temperature. And that answers a lot of questions. That answers the final temperature of the copper. That answers the final temperature of the aluminum. They're the same. So the answer to both is 72.2 degrees Celsius. If I were to ask you to calculate the heat flow, you could also calculate the heat flow.